Hello everyone, myself Dr. Swami Shah. Today I am going to give one lecture regarding the fundamental property relation between commonly encountered thermodynamic properties under chemical engineering thermodynamics and the course code is PCCHE 402. Now, for the fundamental property relation, actually determination of different thermodynamic properties of a fluid that cannot be measured directly, which requires to measure that particular fundamental properties according to the measured variables. Okay, so now for the measured variables, few thermodynamics properties which are actually known as the new thermodynamic properties will be discussed in this topic, as well as what will be the relations, what will be the steps to correlate with each other, that also will be discussed. Now, where we can apply those particular thermodynamic fundamental properties, and basically to determine different numeric values of heat and work in the industrial important purposes. There we can apply those thermodynamic relations, where first we have to identify which will be the unmeasurable variables or unmeasurable properties which we can be replaced with the measured one. Okay, now before going to analyze that particular relations of the different new thermodynamic properties, like like energy properties or reference properties or derivative properties. So very beginning, first we have to recall that first of thermodynamics, where also different types of energy, means like thermodynamic properties are actually involved. Now, in the first law of thermodynamics, which is actually known as the energy neither be created nor be destroyed during a process, it can only change the forms by which we can get one important thermodynamic property as the dE, which is the change in energy involved in the system, and which is the actually difference between the del Q and minus del W, where del Q is the change of heat involved in the system, and del W will be the work done involved or implemented on the system. And on the other side, another one important thermodynamic property which actually cannot be measured directly, that is basically reflected with the help of second law of thermodynamics. Okay, and in the second law of thermodynamics, which leads to expression that involves inequalities. Okay, inequalities, basically, if we consider one irreversible heat engine for an example, which will be less efficient than the reversible one, and that differences involved in the irreversibility or from the reversible one, which will give you the process inequality, which is nothing but that cyclic integration of degradation of heat according to the temperature or with respect to temperature, which is always less than equal to 0. Okay, and this inequality is valid for all cycles like reversible, irreversible processes, or also it is valid for internally reversible one, which is ds is equal to del q by t at internally reversible condition. Okay, and if we rearrange this equation 6, we can get dq reversible is equal to tds, or for n number of moles that will be tdns. So in the first law of thermodynamics, which is giving that equation del q minus del w equals to del E, or that total energy, Okay, so this is known as the total energy. Okay, the total energy, which is the summation of all the macro energies, micro energies, and as well as for which is also related with the internal energies. Okay, so total energy basically is the summation of macro energies and the micro energies. Macro energies means that those energies which are actually related with the or which are depending on the outer references, and micro energies which is totally related with the molecule level. Okay, so that del E or dE, which is the summation of macro energies and micro energies. And if we consider one closed system where all the macro energies will be neglected, only micro energies will be involved, and micro energies actually totally related with the del U, which is known as the internal energy of the system. So dQ or del Q minus del W is equal to del U, which we can get, or this relation, fundamental relation, or the energy relation we can get from the first law of thermodynamics. And this equation dq equals to tds or tdns will give that information about the entropy from the second law of thermodynamics, and that entropy which is not directly measured by the system. So here few derivations or derivation by steps are given as the dq equals sorry du equals to dq reversible plus dw reversible process, and dq is equal to td ns. Now if we consider dq du equals to dq plus dw, where n is the number of moles present in the system, and dq equals to tds or tdns, means like if we replace the dq with the help of tdns, then we can get that equation of the 30 accordingly. Like this will be dnu equals to ddns minus pdv, so pdnv. Okay, where u is v are the molar values of the internal energy, entropy, and the volume, and all other parameters or the properties like p, v, t, s, u, all are included in a single equation. So that's why this is basically considered as the fundamental property relation of the thermodynamics or of a fluid. Okay, so this equation number 13 will be the first fundamental property relation where we can get or we can get the idea about the different thermodynamic properties like pressure, volume, temperature, entropy, and internal energy. Means both that references properties as well as for the energy properties. Okay, so P, V, T, all are the references properties and according to means fundamental properties as well as compositions. Chemical compositions are also considered under the reference properties. And ASU all are basically related with the energy properties. Okay. Among them, U will be the more prominent to consider the energy properties. Now, on the other side, for the enthalpy or from the definition of enthalpy, H is actually equivalent to internal energy and the product of pressure volume. Okay, so H is equivalent to U plus PV, which is another one thermodynamic relations where we can get the idea about the enthalpy or the energy property. Okay, and that can be differentiated and which will give the yield as the general expression like dNH equals to dNu plus dDV or dDNV plus NVdP, where small n will represent as the number of moles present in this system or in the flow system. Okay. Now, if we consider the previous equation, equation number 13, where du equals to tds minus pdv, and in the equation number 15 here if we replace this du with the TdS minus PdV, then we can get or we can reduce the equation number 15 to equation number 16, which is dH is equals to TdS plus PdV when n is equal to 1. So this will be dH is equal to TdS plus VdV. Okay, where n is equal to 1. Okay, so this equation number 16, where we can get the idea or we can get the information about H or enthalpy, temperature, entropy, volume, and pressure, which is also another one primitive relation under the thermodynamic properties, also known as the second fundamental equation. Now, another two fundamental relations we can identify with the help of different new thermodynamic properties, or two new thermodynamic properties under the energy properties. Number one, Helmholtz free function energy, or from the Helmholtz free energy of functions. From there also we can get another one fundamental property relation, and next one that will be the Gibbs free energy. Okay, Helmholtz function or Helmholtz free energy basically will give you the information about the amount of useful work present in the closed system at the constant temperature condition, and for the Gibbs function or Gibbs free energy, which from this Gibbs function or Gibbs free energy, we can get the information about the maximum amount of work can be extracted from the system with a constant temperature and pressure condition. Whereas both the conditions or both the cases, volume will be constant. So from Helmholtz function, A, which is actually denoted by the A, that is equivalent to U minus Ts, and Gibbs function G is equivalent to H minus Ts. Okay, so if we differentiate the equation number 17, then we can get another one fundamental relation, which is known as the dA equals to minus ns dt minus pdv. And for Gibbs function, that is dg is equals to minus ns dt plus vdv. So these are the four fundamental equations has been written over here. Number one, du equals to tds minus pdv. Number two, dH equals to TdS plus VdP. Number 3, dA equals to minus NS or minus SDT minus VdV. And number 4, that is dG equals to minus SDT plus VdP. And if you consider n is equals to 1, at that time those equations can be applicable. Okay. Now, these four fundamental relations which can be implemented to identify that relation between the unmeasurable variable with the measured variables, and can be applicable to identify that relations are between heat temperature, pressure, and the volume, temperature, pressure of the fluid, to determine the heat and work done of a system in industry purposes also. Okay, but if we want to apply those equations, these fundamental equations directly, at that time only we can face one problem to identify the entropy term. Okay, so which is actually not determined directly. Okay, so now to determine those fundamental properties relations or fundamental properties which cannot be identified, which cannot be calculated directly, for this we have to do some partial differential equations. Okay, means like partial differential equations can be implemented to identify or to get that relation, or by which we can replace that not measured or unmeasured variables with the measured one. Okay, and for this Maxwell relation can be considered. Okay, and with the, for the Maxwell equations, that all the Gibbs function, or all the fundamental relation, which is also known as the Gibbs relation, Gibbs equations, can be formed like dz equals to m dx plus m dy, like this mathematical representation. And if we do the exact derivation and the partial derivation, then we can get different mathematical expressions of fundamental relations with the help of partial derivations known as the Maxwell relations. And for this, like four fundamental relations, we can identify with the thermodynamic properties of like reference properties, inertia properties. And if we do the partial derivations of these four fundamental relations or key relations, then only we can get the Maxwell relations, which will give that information about the determination of, not determination, means like calculation of uh, unmeasurable variables with the help of mixer one. And this is the step to determine the Maxwell relations with the help of partial derivatives. And first Maxwell equation we can identify from the first fundamental relation, that is d equals to tds minus pdp as n is equal to 1, where with the help of exact differential of u with respect to entropy at constant volume, and that exact differential equation of u with respect to volume and constant entropy. Okay, and also if we do the partial differential with respect to volume at constant entropy and with respect to constant entropy at constant volume, we can get the first Maxwell equation as del T by del V at constant entropy is equal to minus del P by del S at constant volume. This is the first Maxwell equation which can be identified with the help of first fundamental property relation. And these are the four Maxwell relations with the help of four fundamental relations, and that is del T by del P S equals to del V by del S P. Second one, del S by del P at constant T equals to del P by del T at constant P. Third one, del V by del T at constant P is equals to minus del S by del P at constant temperature. It will be the fourth one. And there, these Maxwell equations are extremely valuable in thermodynamic criteria to give the information or to give the calculation procedure of the change in entropy which cannot be measured directly. And now another one is like industrial application of Maxwell equation, which is to identify the change in enthalpy at phase change condition. Okay, so with the help of third Maxwell equation, we can get the idea about the enthalpy change of a phase change operation of a fluid, where vaporization condition or heat of vaporization that is actually involved. Okay, and this equation will be basically known as the Clapeyron equation, which is del P by del T at saturated condition, as we are considering the phase change operation, is equals to enthalpy change by T into change in volume. Okay, and this is an important thermodynamic relation to identify the change, how much amount of enthalpy change is involved during the vaporization process at a given temperature condition. Okay, alright. So with the help of that Maxwell relation or the thermodynamic property relations, we will be able to identify how much amount of enthalpy change is involved during the phase change operation. And now, if we consider the phase change operation at that time, del V, which is actually the difference between the volume at gaseous phase to volume at liquid phase, Vg minus Vf, where the delta V will be actually tends to Vg. Okay, by neglecting the volume at the liquid phase. And if we apply this condition, and if we consider that Vg will follow or behave like the like Vg means like this, in this condition gas will be behave like the ideal gas, then also that Clausius equation can be rearranged by the Clausius-Clapeyron equation, and the final form of the Clausius-Clapeyron equation, which is this one, like ln P saturated condition of the second phase, like phase 2 to phase 1 is equal to del H by R at 1 by T1 minus 1 by T2. So now, so these are the uh, example of Maxwell relations or Maxwell equations which can be implemented for the real condition, and as well as that Maxwell relations which is basically related with the fundamental property relations, and those fundamental property relations also can be applicable, means like can we can apply those fundamental property relations to identify what will be the enthalpy change in the phase during the phase change operation of a process under the industrial purposes, also as well as what will be during the phase change operation if we means consider that means like volume change, which is basically delta V that I have just uh, discussed, like delta V which will be actually equals to Vg, that volume at the gaseous phase, minus Vf, that volume at the fluid phase or liquid phase, where that Vf we are considering as the uh, means like we are neglecting it as which will be equivalent to the Vg, that delta V, and this delta V also can be replaced as the Vg in the equation number 29. Okay, and this kind of exam means like implementation also we can be we can use in the real case studies, which basically coming from the fundamental thermodynamic fundamental relations. Okay, and now again, like as we are considering the Vg, okay, so at very low pressure condition, okay, so that in this case Vg will be equals to RT by P saturated condition. As we are, it means again I am saying like we are considering the saturation condition which will be very below to the critical point. Okay, so now if we replace that Vg in this equation number 29, then we can get delta P by delta T at saturated condition will be equals to P saturation multiplied by delta H by RT square. Okay, which is giving the equation number 30. And now, if we simplify that equation number 30, then simplify means like delta P saturated by delta T, and P will be coming at the in this side in this condition. And if we do the integration, then we can get the final form as the ln P2 at the saturation condition by P1 at the saturation condition is equal to delta H by R into 1 by T1 minus 1 by T2. And that 32, equation number 32, which will give or equation number 31, means like equation number 32 is the rearranged version of the equation number 31. So both are basically related with the Clausius-Clapeyron equation. Okay, so in the before that the like Clausius equation, that is basically give the information about the enthalpy change of the during the phase change operation, and as in phase change operation we are considering where delta V is tends to Vg, based on that that Clapeyron equation will be modified as the Clausius-Clapeyron equation. Okay, and this Clausius-Clapeyron equation also will be applicable to identify what will be the temperature range, or if we know the temperature range, then what will be the enthalpy change operation going on during the phase change condition.